So without wasting much time, I welcome you once again, Ajay, and pass on to you for the webinar.
Thank you, Dr. Jha, for the introduction, and Happy New Year to everyone as well. So my focus on the talk is going to be, I'll start with basics of some acid, base, and buffering, and then we'll talk about the chemical buffering and kind of give some examples with some numbers to kind of show how amazing the buffering from the body as well as the buffers, phosphate as well as bicarbonate is for the human body. We'll talk specifically about the PCO2 and bicarbonate combination as a buffer because they are the main buffer for the human body. And then we'll talk about the renal acid excretion. And then at the end, we'll talk about acid-base regulation. So just a little bit basic in terms of the laws of mass action and the Henderson-Hasselback equation. So HA or any acid can dissociate into H plus and an anion, and the Ka, which is the constant for this reaction, can be written as H plus with the anion divided by the acid concentration. So if you have a strong acid like HCl, it will dissociate completely in water, and because it is completely dissociated, it will not take up any H plus or be good buffer at all. In comparison, weak acids are partially dissociated. So if you add or give H plus into the solution, they will bind with the anion and make the acid. If the H plus concentration is low, then they will dissociate and release H plus into the solution. So weak acids are actually, or partially dissociated acids are actually good buffers. So a little bit more, the pH is the negative log of the H plus concentration or the hydrogen ion concentration. And if you're looking for the pH with a specific base acid combination, then it will be the pKa, which is the negative log of the constant for the reaction, plus the log of the base and the acid concentration that is in the solution. So for example, we are using phosphate for this. The pKa for the phosphate is 6.8, and 6.8 pH is equal to 160 nanomole per liter. It's important to keep in mind that we are talking nanomolar concentration for the pH, and we'll come back to that a little bit more. So just to kind of have a sense of what the concentration of pH and H plus ions are, it's easy to remember the pH of 7.4 is equal to 40 in the H plus ion nanomole per liter. And then as the pH goes down, so 7.3, you can multiply it by 1.25 to get the H plus concentration for that, because this is a logarithmic scale. And so to go from 7.4 to 7.3, the H plus ion concentration will have to increase to 50, to 7.2 will be 63, 80 for 7.1, 100 for 7, 125 for 6.9, and 160 for 6.8. And the reverse is when your pH is going up. So the H plus concentration will go down, and you can multiply the previous H plus concentration by 0.8. So 40 into 0.8 will be 32, 32 into 0.8 will be 26, 26 into 0.8 will be 20, 20 into 0.8 is 16. So with each step, you can calculate, if you want, the pH as well as what the H plus concentration will be for that particular pH. So now let's look at the chemical buffering. So let's take a solution with 1 liter with 10 millimolar phosphate, hydrogen phosphate, and then 10 millimoles of dihydrogen phosphate. So the H plus concentration for this, so we'll just look at the equation. So the Ka multiplied by the dihydrogen phosphate divided by the hydrogen phosphate. And in this case, as we've taken 10 and 10, so it'll be 160, which is from the previous slide with the pH of 6.8, which is the pKa, which is equal to 160 nanomoles. So in this situation, it will be 160 multiplied by 10 by 10. And if you have equal concentrations of both, then your pH will be the same as the pKa for a particular acid-base combination. So in this case, the H plus concentration will be 160 nanomole per liter, and the pH will be 6.8, which is the pKa for this combination of acid-base. So now let's add 2 millimoles of hydrogen chloride to it and see how buffering works. So when we add 2 millimoles of hydrogen chloride, it will bind with the hydrogen phosphate and become dihydrogen phosphate. So 2 millimoles of hydrogen chloride will bind with 2 millimoles of hydrogen phosphate and make an extra 2 millimoles of dihydrogen phosphate. So what will end up happening is you'll have 8 millimoles of hydrogen phosphate already have. So the hydrogen concentration will be 160 multiplied by 12 by 8. So that will be.
Ajay, you seem to have gone away from your microphone. If you could come back.
Hello.
Yes, this is
Can you
better.
hear?
Yes.
Oh, sorry. So the hydrogen ion concentration would be 160 multiplied by 12 by 8, and that will be 240 nanomoles per liter. And 240 nanomoles would be a pH of 6.62. So now if we look at, we added 2 millimoles of hydrogen chloride, which is 2 million nanomoles, and that has been buffered with an increase of H plus of only 80 nanomoles. So you started with 160 nanomoles and you are now at 240 nanomoles. And so the increase is only 80 nanomoles, whereas you had added 2 million nanomoles. So actually 99.99% of the H plus that was added has actually been buffered. And the pH or the H plus ion concentration has only gone up by 80 nanomoles. So this chemical buffering is a very strong and efficient system in buffering for the human body as well. So the buffers, whichever buffer you're looking at, this graph is for the phosphate buffer that we just talked about, with the pKa being at 6.8. But this is true for any acid acid that you look at, that there is a very linear curve above and below the pKa, where it works as a very efficient buffer. But as you go beyond, so if you look at in this situation, go beyond 8, it doesn't buffer well at all, and there is a rapid increase in the pH with even small decrease in the H plus concentration. And the same is true on the reverse side, where the pH will drop very rapidly or even small increases in the acid addition to the solution. So the buffers are very efficient, plus minus 1 in the pH from their pKa. So now let's look at bicarbonate. So if you look at the reaction of carbonic acid H2CO3, and it dissociates into H plus and bicarb, the pKa for this reaction is actually 3.57, and the pH in the body is 7.4. So actually, this should be a very ineffective buffer for the body. However, there is CO2 which is in the body, which will dissolve in the water or dissolve in plasma and mix with H2O to make carbonic acid as well, and with help of carbonic anhydrase, and then that will dissociate into H plus and bicarb. The pK of the reaction from dissolving CO2 to carbonic acid and carbonic acid to the bicarb is such that there is actually very little carbonic acid. So for every 340 moles of CO2, and 6,800 moles of bicarb, there is 1 mole of carbonic acid. So in this situation, we can also consider the H2CO3 to be not there at all and go directly for a reaction of CO2 plus water that equilibrates with H plus 4 and the bicarb. And the pKa for this reaction is actually 6.1, which is close to the pH of the body. Another part of this, which is why the bicarbonate buffer is good, is that the PCO2 can be blown off by the lungs, and we'll come back to that as well. So this reaction can also be written as the H plus concentration is equal to 24 into the PCO2 in millimeters per mercury divided by the bicarb in millimoles per liter. The reaction can also be listed in the Henderson-Hasselback equation as the pH is equal to 6.1 plus log of the bicarb divided by 0.03, which is the dissolution constant for the CO2 and the partial CO2 pressure. So at a PCO2 of 40, which is the usual concentration of CO2 in the artery, the dissolved CO2 is 0.03 into 40, which is 1.2 millimoles per liter. So now let's talk about why CO2 and the bicarbonate combination is a good buffer. The one main reason is that the PCO2 can be regulated by increasing and decreasing the alveolar ventilation. And the other part is that the plasma bicarbonate concentration is higher in the extracellular fluid compared to any of the other concentrations for other buffers, compared to phosphate or other weak acids which are buffers in the body. The plasma bicarbonate concentration is a lot higher. And so this combination that the CO2 can be blown off through alveolar ventilation or accumulated by decreasing it, and the plasma bicarb concentration is high, is why the CO2 bicarbonate acts as a good buffer. So now let's use this in an example and see how bicarbonate buffering works and some of the other things that go along with it. So 1 liter of plasma with 40 nanomoles of H plus ions, which is the usual concentration in the body, and 24 millimoles of bicarb. The CO2 pressure is going to be 40 millimeters of mercury, which with the dissolution constant of 0.03 will mean that there is 1.2 millimoles of CO2 in the plasma. So using our equation, the H plus is equal to Ka multiplied by, so in this case we are using the dissolved CO2, so we are using the same units, millimoles per liter, for both the CO2 as well as the millimoles per liter for the bicarb. So, so the H plus would equal 800 multiplied by 1.2 by 24, which would be 40 nanomoles per liter, which is our current pH of 7.4. So now let's add acid to it, or let's try and calculate how much HCl we would need to add to change the H plus concentration from 40 to 80, which would mean that the pH would change from 7.4 to 7.1. So to do that, we would have to estimate the HCl, the amount of HCl we would add. So the final H plus concentration that we want is 80, and the 800 is our constant. If we add X millimole of HCl to it, that would add acid to the CO2, and so 1.2 plus that, and it would decrease the bicarb by the same amount, so 24 minus X. So when we solve for X, you get 1.1 millimole per liter. When you add this 1.1 millimole to the current CO2 that is there, which is 1.2 millimole, you will get a total CO2 of 2.3, which as we already know, with the dissolution constant of 0.03 would mean that the PCO2 would have gone up to 77 millimeters of mercury. Another part to assess in this is that When we added 1.1 millimoles of HCl, which is 1.1 million nanomoles, it got buffered excellently, and the increase in the H plus concentration was only 40 nanomoles. Was 80 nanomoles, sorry. And so again, the buffering is excellent and at more than 99% for this. So, however, with 1 millimole per liter addition of H plus, the pH dropped from 7.4 to 7.1. So this is still, even though it's very good buffering, it is still not good enough for the human body. So what does the human body do? It doesn't keep, it has ability to regulate the CO2 and increase the alveolar ventilation, so the CO2 goes down. So now let's recalculate with a situation in which the CO2 is kept constant at 40 while we add extra HCl. So in that situation, what would happen is, if we keep the CO2 constant at 40, then with a final concentration of H plus at 80, we solve again for X with keeping the PCO2 constant at 1.2, and what you get is 12 millimoles per liter. So 80 is equal to 800 into 1.2 by 24 minus X. So this will be 10 into 1.2, which will be 12. So 24 minus 12 is going to be 12. So 12 millimoles. So what ends up happening is, if we keep the CO2 constant, you have an 11-fold increase in the buffering because of this change, where you can now blow off the extra CO2 that is formed by the buffering that has happened. If, in addition to keeping the CO2 constant, which is already being done, if we increase the alveolar ventilation and bring the CO2 down from 40 to 20, which is what respiratory compensation is in our metabolic acidosis, then you can buffer up to 18. You would need 18 millimoles to increase the H plus concentration to 80, or decrease the pH from 7.4 to 7.1. So again, this ability to blow off CO2 dramatically increases the amount of buffering that is happening in the body. So now let's talk about the other steps in the body to maintain pH. We talked about the first step, which is the chemical buffering that is happening by phosphate as well as bicarbonate buffers. Then we talked about the control of PCO2 by alveolar ventilation and how that impacts the amount of buffering. And then the control of the bicarb, which is done through the kidney. And we'll talk about these next. So the concentration of H plus in the body is 40 nanomole per liter, which is the pH of 7.4. It is important to keep in mind that this is a million-fold lower than all the other ions. So sodium, potassium, bicarb are in millimoles per liter, while the pH or the H plus concentration is 40 nanomoles per liter. And it is very important to keep it tightly regulated, because any significant changes will lead to problems in protein function and changes in the protein function as well. So the normal acid production that is there, so there are two components to it. One is from the metabolism of carbohydrates and fats, which produces 15,000 millimoles of CO2 every day. So the body has to get rid of that every day to make sure the pH remains stable. And then in addition to that, there are the non-carbonic acids, which are produced by metabolism of proteins like sulfur containing amino acids, which would generate sulfuric acid. And this acid load is about 50 to 100 millimoles on a normal Western diet. So to maintain acid-base homeostasis, the body needs to get rid of the 15,000 millimoles of CO2 and be able to excrete the 50 to 100 millimoles of daily acid that has been taken in. So in terms of the buffering in the body, proteins, organic as well as inorganic phosphates and hemoglobin are there in the intracellular compartment. And then in the bone, the hydrogen ion can be buffered in replacement with the surface sodium and potassium, as well as dissolution of the bone mineral calcium carbonate and calcium phosphate, and that can then buffer the acid load as well. It is estimated that about 40% of the acute acid load is buffered in the bone, but that this may be greater in chronic acid loads, such as in chronic kidney disease, and is one of the components of why there is bone disease in chronic kidney disease and loss of bone mineralization in that situation. So now this is some of the dog studies that were done to see what is happening in real life. And what they did was they added 180 millimoles of hydrogen chloride to each dog. The dog weighed about 19 kgs and their volume of distribution was about 11 liters of fluid volume, water. If there is no buffering, then the H plus concentration would have gone up to 16, and the pH would have gone down to 1.8, which no one can survive. In real life, what actually happened was the pH dropped from 7.4 to 7.07, which means that the H plus concentration was only 86 nanomoles per liter. And the bicarb dropped from 24 to 7, and the PCO2 dropped from 40 to 25 in the respiratory compensation that happens with metabolic acidosis. So based on this and other calculations, they estimated how much buffering is happening in different parts of the body. And what you can see is in metabolic acidosis, about 57% of the buffering was inside the cell, and 43% was extracellular. With the majority buffering extracellular being done by the bicarb buffers, bicarb and CO2, and the exchange for potassium and exchange for sodium were the main cellular buffering that was done inside the cell. Similar studies were also done for respiratory acidosis buffering, and we'll come to what they found in there. You have two components when you have respiratory acidosis. The first component is an immediate rise in the plasma bicarb. So as your CO2 goes up, it makes more carbonic acid. That dissociates into a higher bicarb and H plus concentration. The H plus then gets buffered by the cells and the bone in replacement for sodium and potassium. The H plus can also be buffered by hemoglobin and then release the bicarb from the RBC into the plasma. And for every 10 increase in PCO2, the bicarb increases by about 1 from this mechanism of immediate buffering that is happening. The longer term buffering happens by increased renal excretion of H plus, and that is about 4 per every 10 of PCO2. So now let's just talk about if the PCO2 goes from 40 to 80 and the bicarb remains same at 24, then the H plus concentration is 80 and the pH has gone from 7.4 to 7.1. With this immediate buffering, for the rise of 40, the bicarb would go up to 28, and that would give you an H plus concentration of 69 and the pH would be 7.17. With the longer term buffering, that happens where the bicarb goes up by 4 for every 10. For a rise of PCO2 to 80, the bicarb would be increased to 40, and the H plus concentration would now be 48, which would be a pH of 7.3. So that means that a pH of 7.1, if there had been no buffering, is stabilized to 7.17 by the immediate buffering from the bicarb, and then with the renal adjustment that happens over days, it gets buffered to 7.3. So again, with the dog studies, what they found was the majority of this buffering was in the cellular compartment, with 37% being buffered by the sodium, 14% by potassium, and then the bicarb chloride exchanger was responsible for about 29%. So 97% of the buffering was cellular buffering. So now let's talk about the renal acid excretion, which maintains the bicarb component of the buffering. So when we talk about the renal acid excretion, there are multiple parts to it. The first job that the kidney has is to reabsorb all the filtered bicarbonate. Then after having done that, it must excrete 50 to 100 milliequivalents of the non-carbonic acid that is the load of the day. And this is achieved by secreting H plus ions. However, we cannot just excrete plain free H plus ions because the pH would then become extremely low in the urine, and that would not be possible to do without damaging the surrounding tissues. So it has to be excreted with filtered buffers, which are phosphate, creatinine, and ammonia, which forms the ammonium ion. Ammonia is very important because the rate of ammonia production as well as for ammonia excretion can vary as per the need of the body. In addition, the extracellular pH is the main regulator of acid excretion, though volume, aldosterone, and potassium can also affect acid excretion. So now let's talk about each of these aspects in more detail. Another part of this is that the acid excretion actually, like all other things that we've talked about, sodium, potassium, reaches a steady state. So if you look at, and this study is done in multiple individuals where they looked at their acid excretion and acid intake and acid production. So on the y-axis is acid excretion and on the x-axis is acid production, and it is a straight line and they're in balance. So if you take in more acid, the body adjusts itself to excrete more acid. If you take in less acid, the body adjusts itself to excrete less acid. So how does the body do that? That's what we're going to talk about. So in terms of reabsorbing the bicarbonate, so let's just do some numbers. The GFR for an individual is 180 liters per day, and a plasma bicarbonate of 24 milliequivalents per liter is filtered every day, is the concentration. So the total filtered bicarbonate is 4,300 milliequivalents per day. So that's the first job of the kidney, is to reabsorb all of this 4,300 milliequivalents per day. So how does the kidney do that? It does that both in the proximal tubule as well as the distal tubule. In the proximal tubule is what we are showing in this figure here. And the water that's inside the tubular cell will dissociate into hydrogen ion and hydroxide ion. The hydroxyl will combine with the CO2 with carbonic anhydrase and make a bicarb. The bicarb will be reabsorbed with sodium into the peritubular capillary, and this is assisted by energy from the sodium potassium ATPase as well as the charge from the sodium potassium ATPase that is generated as well. The H plus is then secreted into the tubular lumen, which is this side, and in the tubular lumen it will combine with the bicarb and make carbonic acid, which will with carbonic anhydrase get dissociated into CO2 and H2O. So what is ultimately happening is that a bicarb that is in the lumen is combining with an H plus, and we have a bicarb that is getting reabsorbed into the peritubular capillary. So that is how the predominant bicarb reabsorption is happening in the proximal tubule, and that is responsible for about 90% of the reabsorption of the bicarb. In the distal tubule, we have something similar, but the channels and the transporters are different. So the tubular lumen in this side is here. We have an H plus ATPase, which will secrete the H plus into the lumen, and again the H plus will combine with the bicarb and with the carbonic anhydrase make CO2 and H2O. And again, the bicarb here that is generated from the hydroxyl ion with the CO2 is reabsorbed into the peritubular capillary with a chloride bicarb anti-exchanger. So the transporters are different, but the philosophy is the same, where the H plus ion is being secreted into the tubular lumen to combine with the bicarb, and a bicarb is reabsorbed into the peritubular capillary with the chloride bicarb exchanger. So that is how the reabsorption of bicarb is happening. There is also titratable acid which is secreted, and so this H plus secreted into the tubular lumen can either combine with the bicarb, which is what we just saw. It can also combine with phosphate or ammonia, and when it combines with phosphate or ammonia, the bicarb that is then reabsorbed by that mechanism is now a new generated bicarb, and that helps replenish the bicarb that was lost due to the buffering that has happened before. So let's look at that as well. So the net acid excretion of the body is the titratable acidity or titratable acid plus the ammonia that is excreted minus any bicarb losses that are there. Usually the intake is 50 to 100, the excretion is 50 to 100. If someone increases their acid load, this can go up to 300 milliequivalents per day. And if someone has a very high alkali load or has received bicarb infusions or something, then it can also be negative with large bicarb losses. So now let's look at the proximal tubule and collecting tubule in one figure, and the exchangers and the transporters are the same as we talked about the first one with the bicarb. In this case, the H plus that is being secreted into the lumen will combine with the phosphate and make a dihydrogen phosphate, which will get excreted, and the bicarb will again with the sodium 3 bicarb exchanger get reabsorbed into the peritubular capillary. And again, this is the energy for this is coming from the sodium potassium ATPase. In the collecting tubule, you again have the H plus ATPase, which is secreting the H plus, but instead of combining with bicarb, it is now combining with the phosphate, and the bicarb is reabsorbed by the chloride bicarb exchanger in the peritubular capillary side. So the exchangers are the same, it's just what the H plus combines with that now the buffering is with the phosphate, and that now becomes titratable acid. So how does the phosphate, and the phosphate being a buffer, work during the transport from where the phosphate is filtered to when it is excreted in the urine? The pH plays a big role in that. So if you look at how good the pH is and how much of an impact that makes, if you look at the pH of the filtrate has a pH of 7.4. And if we had 50 millimoles of phosphate that was being excreted, because the pH is 7.4, the ratio of hydrogen phosphate to dihydrogen phosphate would be 4 to 1. So 40 millimoles of the 50 millimoles of phosphate would be in hydrogen phosphate form, and there would be none of it that had been buffered. In the proximal tubule, the pH drops to about 6.8, which is the pKa for hydrogen phosphate dihydrogen phosphate combination, and so it will be a 1:1 ratio of 25 to 25. So now you have 15 millimoles of buffering that has happened. When you go to the final urine, if it is an acidic urine of 4.8 or 5, the hydrogen phosphate would be now at a concentration of 0.5, and the dihydrogen phosphate would be 49.5, and so you have majority of the phosphate being dihydrogen phosphate, and so you have buffered of about 40 millimoles out of the 50 millimole of phosphate that is excreted. So this tells you that the phosphate buffer is quite a bit dependent on the acidity or the pH at which the urine is coming out, and the lower the pH, the better the buffering that is being done by the phosphate buffer or the phosphate excretion. So now let's look at ammonia, which is one of the things which can vary by the need of the body. So again, the proximal tubular cell is on the left and the collecting tubules on the right, and the ammonia is actually or ammonium is actually produced from glutamine, which will make ammonium and alpha ketoglutarate. The alpha ketoglutarate will then be degraded into bicarb, which will be reabsorbed, and the ammonia will be secreted into the tubular lumen. The ammonia, being a positively charged ion, is unable to get reabsorbed, though there is some cycling, and we'll talk about that in the next slide. In the collecting tubule, the ammonia actually diffuses through the cell, ammonia, and can be released through the cell membrane, and the H plus ion that is secreted by the H plus ATPase will combine with this ammonia that is floating through the medulla and the medullary collecting ducts, and make an ammonium ion, and the bicarb that is generated will get reabsorbed by the same chloride bicarb exchanger. If you look at the whole nephron, look at what happens to ammonia or ammonium ions. The ammonium that is generated in the proximal tubular cells goes through the loop of Henry, and then from the sodium potassium 2 chloride channel, instead of the potassium, the ammonia can get reabsorbed into the medulla, and then it can undergo cycling. The ammonium can get converted to ammonia and then get reabsorbed, and then it undergoes an intramedullary cycling, so there is a higher concentration of ammonia at the tip of the loop compared to the other parts. So in the concentration gradient, you also now have ammonia, which is getting concentrated. The importance of that is when you have the collecting duct, because now this higher ammonia concentration can get freely diffused into the collecting duct, where the H plus secretion that is happening from the H plus ATPase can then bind with the ammonia and become ammonium, and then it will not get reabsorbed. So the secretion of the H plus ATPase, which is where the control of acid base is happening in the body, can go up or down based on the acidity, intracellular pH, and the acidity that the body is sensing there. Another part of this ammonia excretion is, if you look at the acidosis or the urine pH, as the urine pH goes down, if you look at ammonia excretion in the setting of acidosis, the ammonia excretion is much higher compared to if it was just static ammonia excretion. This slide has the plasma bicarb concentration in the boxes and the ammonia excretion in the circles. And this is a study in which the volunteers did extra and increased their acid intake. And what ended up happening is, with the increased acid intake, their ammonia excretion increased drastically from 40 millicolons per day to 160 millicolons per day. And this was driven by only small decreases in the serum bicarbonate, so from about 24 to about 20. So a decrease in the serum bicarbonate of about 4 had driven the ammonia excretion from 40 all the way up to 160. So it again shows you that in normal human being, where there is no other pathology, even if you increase your acid excretion drastically, the body is able to adjust and adapt and increase its ammonia excretion significantly, with the main difference being small changes in the bicarb, which are read through the small changes in the intracellular pH that is there in the distal tubules. So regulation of the renal hydrogen excretion. So now we'll talk about what are the different regulators for the acid. Any acidemia will increase the proximal and distal acidification. So the intracellular pH, as it goes down, there is an increase in the H plus secretion, or the hydrogen ion secretion, which is from the enhanced luminal sodium hydrogen exchange, um, because of the increased binding of the H plus to the exchanger. There is enhanced luminal hydrogen ATPase activity. There is increased activity of the basolateral sodium and 3-bicarb cotransporter, and there is increased ammonia production from glutamine. So all of these factors help increase the hydrogen excretion in the setting of acidemia. The extracellular pH that is there also causes increased ammonia excretion, and this is thought to be happening due to parallel changes in the intracellular pH. If you have metabolic acidosis, there is an increased ammonia production, and this peaks at about days 5 to 6 after the after the generation of metabolic acidosis. The enhanced ammonia excretion is also by the combination of lowered pH in the distal convoluted tubule in the tubular lumen, as well as the enhanced ammonia generation in the proximal tubule. So it's a combination of both of those which increases the ammonia excretion. So now we'll switch to metabolic alkalosis. So in the setting of an elevated pH, the cortical intercalated B cells can actually insert the hydrogen ATPase in the basolateral membrane instead of the luminal membrane. And so now the H plus is actually being reabsorbed, and the bicarb is being excreted into the tubular lumen to compensate, to correct the metabolic alkalosis. So the bicarb will be transported into the tubular lumen for excretion in exchange for the chloride, and the hydrogen ion is going to get reabsorbed to help correct the metabolic alkalosis. For respiratory acidosis and respiratory alkalosis, the PCO2, that is in respiratory acidosis, the increase in the PCO2 will cause a decrease in the intracellular pH, and that will then cause the increased hydrogen ion secretion and increased bicarb reabsorption. And as we've talked before, in chronic respiratory acidosis or respiratory alkalosis, for every 10 increase or decrease in PCO2, the bicarb will go up or down by 4. The bicarb can also be excreted. So this is again humans, volunteers who have done the study, and the top line is the amount of filtered bicarbonate. So as the so on the x-axis is the glomerular filtrate bicarbonate in millicuries per liter, and on the x-axis is the plasma bicarbonate concentration. So as the plasma bicarbonate concentration goes up, the filtered bicarbonate continues to go up, and the reabsorbed bicarbonate is complete till you reach a bicarb of 26, at which point the reabsorption plateaus and you have excretion, which is at the bottom, that picks up. And so the reabsorption of bicarb plateaus at around 26, bicarb of 26 and above, and excretion starts to happen at that point. However, this excretion and reabsorption can be affected by volume and volume status, which was done in the subsequent study. And in volume depleted individuals, the bicarb can continue to be absorbed even with the bicarb of 35. And so metabolic alkalosis is maintained or can be maintained by volume depletion. So this is depicted in this study that was done in 1960, where again, the circles are where there is minimal expansion in the intravascular volume, and the triangles are where there is an exaggerated expansion. of the intravascular space. So with no expansion, the kidney continues to reabsorb, which is like a volume depleted state. It will continue to reabsorb the bicarb all the way up to 35, while if you are volume replete and otherwise normal, the kidney will not reabsorb above 26. And the same in the reverse is in the excretion, with the triangle showing that there is excretion when there is expansion of the volume with the increase in bicarb, while if you are volume depleted, then the bicarb excretion is minimized. So now the other things that can regulate acid base is the renin-angiotensin-aldosterone system. So in the setting of hypovolemia, your RAAS can increase, and that can lead to an increase in H plus secretion and bicarb reabsorption. Aldosterone also stimulates the hydrogen ATPase in the distal nephron, and also increases the bicarb extrusion via the chloride bicarb exchanger. It can also do it indirectly by stimulating the sodium reabsorption, which helps change the electrical gradient across the membrane and improving or exaggerating the bicarb reabsorption. The plasma potassium is another big factor in regulating acid base. If you have low potassium, what happens is the cell leaks potassium into the intravascular into space in exchange for hydrogen and sodium. When the hydrogen comes inside the cell becomes now acidotic, and that hastens or increases hydrogen ion excretion, which could even be in the setting of a metabolic alkalosis, because the cell inside feels it is acidotic because of the H plus that it has taken in. If you have hyperkalemia, the reverse happens, and the intracellular alkalosis causes reduced bicarb reabsorption or enhanced bicarb excretion. So in summary, humans have an incredible capacity to buffer for acid-base changes. This acid-base buffering is composed of three components: the chemical buffering, which we talked about, the PCO2 regulation, which is through ventilation, and the bicarb regulation, which is through the kidney. The kidney regulation, the first of all, it has to reabsorb the bicarb. Then there is excretion of titratable acid through buffering with phosphate, and then ammonia generation and ammonia excretion. The main regulation or regulator of acid excretion is the extracellular pH, which mostly regulates it through concomitant changes in the intracellular pH. Other regulators are the renin-angiotensin-aldosterone system, the potassium, volume status, which can also regulate the acid-base status in particular situations. I would like to acknowledge Dr. Burton Rose as well as his book, from which a lot of this talk has been made, Dr. Vijay Kher and Dr. Vivek Jha, and I'll be happy to take any questions.
Thank you, Ajay, as usual, for explaining this topic in a very simple and accessible manner. As you described, for those who want to learn more and more about it, one of the most valuable resource is this book by Dr. Burton Rose. This book has been around for a long time. In addition to Ajay, I can confirm actually benefiting a lot from this book. And for those of you who are interested in learning more about acid base and electrolyte disorders, I think you could do worse than going and referring to this book. This book should be actually on the shelf of most nephrologists who are interested in acid base and electrolyte and water disorders. So as usual, Dr. Ajay Kher is absolutely happy to take any questions. Please feel free. The way to ask questions, is to either type your question in the pane, the usual chat pane, and then I will read it out for Dr. Kher, or you can actually raise your hand. using the tool in the GoToMeeting panel. In which case, I will unmute you, and you can go ahead and directly ask your question to Dr. Kher. So please go ahead. We do have quite a few attendees, so I'm sure, as usual, there are going to be more than one question here. Somewhat unusual that we already don't have quite a few questions. Maybe I can start by asking Dr. Kher, what do you think are the most critical points which cause the acid-base homeostasis to break down? As you described, the process is very efficient, and but still, I think there could be some critical components that that might really be important in keeping this all going, and accounting for the fact that there are quite a few redundancies in the system. What do you think are one or two most critical points?
So I think the things that I talked about at the end, the additional regulators that are usually where issues happen. So volume depletion and the combination of that with metabolic alkalosis. So if you have someone who just increases their bicarb, and that's been well studied, the body's capacity to excrete that extra bicarb is incredible. But if you add volume depletion and then you have an increase in bicarb, the body is unable to handle that extra bicarb, or the same is with hypokalemia. So I think it is when there is a combination of factors, then the body has a difficulty in handling this combination of hits, and that's where then the acid-base disorders get more problematic. Or when the kidney itself doesn't get perfusion or is in damage. So when it's shock, or whether it's septic shock or any other shock, then the kidney can't handle that acid load because it's not perfusing itself.
Right. So I think there is a related question from Dr. Manzoor Perry, who wants to know what is the role of chloride in metabolic alkalosis in contraction situations?
So in the setting of metabolic alkalosis, the main question is whether this is volume sensitive or chloride sensitive metabolic alkalosis. And the one way of checking for it is to look at urine chloride. In most situations, we can use urine sodium to assess the volume status as well. However, in the setting of metabolic alkalosis, when the kidney is trying to get rid of the bicarb, because it will also have to get rid of some cation with the anion, so then sodium, being one of the major cations, can get excreted with it. And so the urine sodium may look high because of concomitant excretion with the bicarb, but the person is actually volume depleted, in which case the urine chloride would tell you that that's the case, because the urine chloride would be less than 10 in that situation. So in the setting of metabolic alkalosis, the urine sodium may not be the best readout for someone's volume status, but the urine chloride would help in that situation.